In this, what we want to talk about is we want to talk about the magnetic field possibly doing work on a particle. So when an electric field is applied to a particle, what happens is that electric field pushes or moves that charge, right? So the electric field produces a force upon that particle and thus moves that particle and therefore does work on the particle. Now we want to ask the exact same question. Will a magnetic force do work upon a charged particle? So let's describe what we have here in this picture. We have the X's that are going to represent the magnetic field that goes away from us and into the board, because in essence we're seeing the fletchings from the arrow. We have a charged particle which is going to have a plus Q charge. It has a plus Q charge. And it is moving in a counterclockwise rotation. Now, how is it moving in a counterclockwise rotation? Well, what we want to do is we want to understand the direction of the force from the magnetic field. If you start at the 12 o'clock position and you use your right hand, so we're going to use the right hand rule. If we use our right hand at the 12 o'clock position, remember our fingers are going to point into the board or into the screen because that's the direction in which the magnetic field is going. Our thumb is going to represent the velocity, the direction in which the particle is moving. All right? And our palm in this case is going to be pointed straight down. It's going to be straight down, assuming you're starting at the 12 o'clock position. And so the force is going down. The force is going down in this case. If we move to the 9 o'clock position, once again using the right hand rule, our fingers are pointing into the board, our thumb is pointing down, and the force is pointing towards the center of the circle. And we can do this at the 6 o'clock position, where your fingers are pointing into the board, your thumb is pointing in the direction that the particle is moving, and the force is once again pointed towards the center of the circle. And the same thing at 3 o'clock. We do the 3 o'clock position, we do test the right hand rule there. Our fingers are pointing into the board, our thumb is pointing in the direction that the particle is traveling, and the force is going in towards the center. All right. In contrast to the electric, so that let me describe a little bit more of the picture. Sorry, I was getting ahead of myself. But the force is pointing towards the center, all right? And that force is the force due to the magnetic field. Remember, the force of the magnetic field is going to be perpendicular, or it's going to be the right-hand rule, or it's going to be the cross product of the velocity vector and the direction of the magnetic field. In contrast, compared to the electric field, the magnetic force always acts in a direction that is perpendicular to the motion of the charge. Right? So if the magnetic field in this example is going into the board, that's going to be perpendicular to the direction of the velocity or the movement of the particle. The displacement of the moving charge never has a component in the direction of the magnetic force. Now this particle moves not in the same direction as the force. Therefore, since the velocity does not move, is not parallel to the direction of the force, that means that the magnetic field cannot do work on the particle because it doesn't change the kinetic energy of the particle. And the reason being is because it's not parallel with the force. Since the force is perpendicular to the velocity, the particle changes direction, but not the speed. Right? So it's always changing direction, right? But it's always going at the exact same magnitude. It's always going at the exact same magnitude. All right? Let's do a little bit of math here, all right? Let's do just a little bit of math, all right? Let's talk a little bit about math. And so what I want you to focus on is this force. We're first going to focus on the force. And what we can say then is that the magnetic force, the F sub B, is equal to Fc. And what Fc is the centripetal force. It's the centripetal force. And what we can do now is we can now equate these with each other. All right? Because this force from the magnetic field is going towards the center. That's the exact same thing as a centripetal force. If we and recall that F sub B is equal to Q upon V Q. Oops. Sorry, I made a mistake. The magnetic force is equal to QVB, and that's equal to, now this has to go back to last semester, the centripetal force is mass times velocity squared, all divided by R. We can then solve this equation for R, such that R becomes equal to mass times velocity squared, all upon the charge of the particle times the velocity of the particle times the magnitude of the magnetic force. Now, one of the V's cancel such that the radius, so R is the radius of this circle, is equal to mass times velocity all upon QB. So the equation to find the radius of the circle, in which, in this case, is a plus charged particle, so it could be a proton or a nucleus, is traveling around in a circle, we can find the radius of that circular movement. So once again, I want to go back and answer the question I'd asked before. Does this magnetic force do work upon the particle? And the answer is no. And the reason being is that the velocity vector is not parallel with the force vector, and it does change the angle of it, but it does not change the speed of the particle.